Hello and welcome, everybody, and thank you very much for joining this session on introducing quantum computing with AWS. My name is Eric Kessler, and I'm the head of business development for quantum computing. And it's my great pleasure today to be joined by Fernando Brandao. Fernando is a professor of physics at Caltech and joined AWS this year as our head of quantum algorithms. Fernando and I will give you an overview today about quantum computing and specifically its long-term promise and why it is such a fascinating technology. But also, we will give you a transparent and honest snapshot as to what the big challenges in the field are, where we stand today. And finally, we'll be introducing the different announcement that you have seen throughout this week from AWS in quantum computing. Before we get started, let me quickly mention that there will be a repeat of this session tomorrow at 2:30 p.m. in the Bellagio. And yeah, without further ado, Fernando, please take it away.
Thank you, Eric. Hi, everyone. So I will give an overview of the field of quantum computing, and then Eric will tell us about what AWS is doing in this space. So I want to start working backwards and just give you the summary of the talk first, in case your attention span is like a few minutes. Pay attention to this slide, and then you can check your phone or whatever you want to do. So what is quantum computing? We want to explore the intricate physical laws of the microscopic world to perform computation in novel, improved ways. Quantum mechanics, which describes microscopic worlds, right, is a quite different theory from classical mechanics that we learn in school, and we can use that for technology. So it's a potential for a new paradigm in computing, and it's really not about just doing a 10x improvement in performance or in speed. It's really about like a 10 to the x. So it's a qualitative change, and it just means that some problems that are out of reach today, we could solve them once we have a quantum computer. But there is really hard scientific and engineering challenges ahead to build a quantum hardware at the scale that we need and that we would like to have one day. But we are just entering what people call in the field the noisy intermediate scale quantum era, or NISQ era. So this is still quite far away from the ultimate goal, but it's already promising for early explorations. And I want to tell you where we stand there. So when we talk about quantum mechanics, and we say, oh, this is very far in the future technology, but that's not the case. Actually, many of the technological breakthroughs from last century, it was crucial that we understand quantum mechanics. So 3 examples. One is NMR, right? So for NMR machine to work, we have to understand how nuclei respond to magnetic fields. We need quantum mechanics for that. If you want to have a laser, we have to understand how photons work, right? So we have to quantize lights, quantum mechanics again. And even our modern computers, right? We need transistors. And for that, we have to understand semiconductor physics, which is all about quantum mechanics. So, we do need quantum mechanics, but we really want to more of tame the quantum effects in the material and just do and use them to perform like a classical logic, right? Or to perform technology in the way they understand before. What we want to do next moving forward is really not tame these quantum effects, but really explore them to our use. Okay, so why we might believe that it's interesting to use quantum mechanical systems for computation? That really came from observation that people that have to use quantum mechanics day by day, scientists and engineers, know for a long time. So let me show you a plot. This is the use of the Department of Energy supercomputer by Area in 2018. And then you see, right, like there's like the first one, Earth environmental systems, has nothing to do with quantum mechanics. But then chemistry, a lot of quantum mechanics there, material science, nuclear physics, and so on, high energy physics. So a large fraction is devoted to simulating quantum systems. Why that's the case? Well, as we'll see a little bit later, it turns out that the cost to simulate a quantum system grows exponentially with the size of the system. So it takes 2 to the n steps to simulate a system with n qubits. What is a qubit? I'll tell you in the next slide in more detail, but it's just the basic units in quantum mechanics. Is like a 2-level system. You can be a photon in 2 different polarizations or electron in 2 different states. This exponential growth is because of a phenomenon that we call entanglement that can happen in quantum mechanics. It doesn't happen in classical mechanics. So in pragmatic terms, it means that if you want to understand a system with 30 qubits, this takes 16 gigabytes. If you want 40 qubits, 16 terabytes. 50 qubits already 16 petabytes. And if you already have only 333 qubits, that's 10 to the power of 100, which is more than the number of particles in the visible universe, right? So it's really, there's this very fast growth. And that's a challenge. And actually, the first one to point out to this challenge and see that maybe there is a better way of studying these quantum mechanical systems was Richard Feynman, who was a physicist at Caltech. In '81, he gave this quote. He said, trying to find a computer simulation of physics seems to me an excellent program to follow out. Nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy, right? So he had like this pioneering insight that it's so hard to simulate these quantum systems when the size of the system grows. Maybe we should actually use quantum mechanics itself, quantum systems themselves, to build a new type of computer, and maybe this will give a better way of doing material science, doing chemistry, and so on. Okay, so now let me just tell you a little bit. This is the only slide with some equations, but just in case you're curious, right? What is a qubit that I mentioned before? This is the basic unit in quantum mechanics and in quantum computation. We use what we call this bracket notation to denote the state of the system. So this is like the state psi of a qubit. And it's a very simple object. It's just a two-level system. There's like the 0 and the 1, the same way as a classical bit. But now the difference is that you can be in a superposition of 0 and 1. So you can have what we call amplitudes. It's like alpha and beta here. And the general description, as far as we know from quantum mechanics, is like a superposition of these two. But what it means, right, to be in a superposition, well, it's subtle. If you actually go and observe the qubits, you never see the superposition. You either see the qubits in the state 0 or in the state 1. And you see each one with a probability. How we compute this probability? Well, you get the square of the amplitudes. So alpha square is the probability of you measure 0. Beta square is the probability that you measure 1. So if you think about it, just from what I told you, this is really very similar to a probabilistic classical bit, right, where you have some probabilities of being 0 and 1. But because actually they can be superposition instead of just like some probabilistic mixture, you can have vastly different phenomena there. So amplitude instead of probabilities make a huge difference. So you can have unique features like interference between qubits, entanglement between qubits. And this is what we explore in quantum computation to do novel things that we couldn't do otherwise. So an n-qubit system, just write the equation, right, is the same way you write one qubit, now you have n of them, but you have the C coefficients, right? This is like, you have one coefficient for each of the base elements, and there are exponentially many of such coefficients, right? And that's why, the description increases with time very fastly. There are better ways to model many systems, but as far as we know, the general one, we have to use all these coefficients, and that's right. That's the exponential cost that I mentioned before. Okay, so what is the quantum technology that we would like to build in this century, right? And this is really, we would like to have quantum computing. So quantum computing uses well-controlled quantum systems for computation, right? And what is the way to think about that on the most basic level? Well, let's take as an analogy a Boolean circuit, right? That's how we use in our computers today. And then we want to break out a computation, a complicated procedure or an algorithm, into just a sequence of basic gates, right? They can be like OR gates or AND gates. And here's an example of a very simple circuit to compute, just this simple Q function, AB plus BC times B plus C. Quantum computing, we want to do the same. So we want to have some complicated algorithm that we want to implement, and we want to break it down. Again, it's a circuit, but now it's a special circuit because we can use basic elements which only controls one qubit or only control 2 qubits. But because quantum mechanics, right, we can use a richer class of gates. So here's a simple example which just creates a kind of an entangled state between 3 qubits. This is not good algorithm for anything, but you see that it's a richer class of algorithms that we can have access to. And it turns out that there are many interesting applications, as I will mention in the next slides. But before I turn to the applications, let me tell you, okay, this is very abstract, right? This is how we write a quantum computation on a piece of paper. But how we actually build this, right? How we actually implement this physically. And there are many labs and many industrial efforts trying to do this today. And I want to mention 4 examples. There are other important examples like quantum dots or NV centers that are also going strong. But let me focus on these ones. So the first one is what we call superconducting qubits. So the idea there is that you encode the qubits into a macroscopic states of many electrons. So these many electrons, they can be in between like two superconductors, and they can oscillate between the two of them, and there you can encode the qubits. So that was like the original motivation for building this, is that you could have this kind of macroscopic system in a quantum state, which is cool. But it turns out that they're pretty good for building quantum computers, because you can just print them on a chip. You can control them with microwave control, with like cables. You need pretty cold temperature. It's like a few millikelvin away from the absolute zero. So you need a big fridge, right, and put this guy inside. But it's a promising approach. Another one of the oldest one actually, is to use to encode the qubits in atoms. So atoms, they give pretty good qubits. You can have like an electron in an atom and use two energy states of this electron. And you can have like pretty low noise, so they are nice. You can control them with lasers. But how you couple these atoms, right? One way in trapped ions, you just use charge atoms, so you use ions. So they, right, the Coulomb interaction, they repulse each other, or they attract each other. So if one wiggles here, the other wiggles here, and that's how you couple them. There is an interesting effort in this direction. Another way to use atoms, what we call Rydberg atoms, you just put them on a very highly excited level called Rydberg states, and that's highly interacting between nearby atoms. People also try this. That's like a nice example of how you can create an Eiffel Tower, right, from these neutral atoms. And finally, some people are exploring how you can use photons to do quantum computation as well with silicon photonics. So it's fair to say that each one of them, they have their strengths. Each one of them also have big challenges that we have to overcome if we are going to one day build a scalable quantum computer out of them. There is no clear winner at the moment. There are many people, and they're excited about each one of them and really trying hard to figure out the technical challenge. And I think that's healthy, right? And I predict this will stay for a while. And it's not even clear, right? Classically, we had the transistor. This was clearly the winner, right? Over vacuum tubes or whatever else people tried. It could be that the same happens quantum. It could be that it doesn't, right? It could be that there's always like alternative technologies, and they have their own merits. Very good. So, we really want to build this quantum computer using this technology. I'll tell you later on where we are at the moment. It's still quite ahead from where we want to get. But let me spend some time just telling you why we care about this, right? Why we really want to build these quantum computers. And this is about the applications, right? What can we do with these machines once we have them at enough scale? So these are applications of quantum computing. So I want to give you a few examples in different areas. The areas that people have figured out applications, and that was a very surprising thing, right? They're vastly different from this original motivation from Feynman of just trying to model or to explore and study quantum mechanical systems better, right? So they're very widespread. So it goes from cryptography to, again, physics and chemistry simulation, as I mentioned before, to material science, and to optimization and operations research. So what is an example in each one of them? So for example, famously, in 94, we learned that we can break RSA, right, the most used public crypto system, if you had a quantum computer. This, we need like 6,000 qubits for that. Another interesting application is to simulate a molecule called FEMOCO. It's very important for like creating better fertilizers. This will require 200 qubits. If you want to simulate new interesting kind of materials, for example, high temperature superconductors, this will take from 70 qubits onwards. And in optimization, there's like widespread applications from searching, ranking, learning, minimizing, and this takes like from 100 qubits onwards. So you see pretty small number of qubits, right? You could have these major breakthroughs. That's very different, right? With 200 bits, what we can do with that, not much, right? But there is a catch, very important catch. I'm assuming that you have perfect qubits with no noise for these estimates. And this is not the case, right? So these numbers actually are not the numbers we should have in mind. I'll tell you them very soon. Before I do that, let me dive deep a little bit into some of these applications, just tell you a little bit more about them. So let me start with cryptography, because maybe that's what you heard about before. It's one of the most well-known applications of quantum computers. So it turns out that the security of this RSA protocol that I mentioned before is based on the fact that to factor large numbers is a computationally hard problem. What is factor? Well, we all learn in school, right? So if I give you 15, we can write this as 5 times 3. So these are the prime factors of 15. But if I give a really big number like this one that I wrote there, then I can tell you that if you multiply the two other numbers on the right-hand side, you get the big number. So you can multiply quickly, right, in a calculator or even in your head or a piece of paper. But how do you do the opposite? That's very time-consuming, actually. So as far as we know, the best way of doing that for an n-digit number, the cost is very big, grows exponentially in 1.9, the cubic root of n. So if you have already like to factor a number with 2048 digits, like what's used for RSA, this will take like a quadrillion years in the current estimates of supercomputers that we have. So it's out of reach, right? And that's why we trust this protocol. That's why we use it a lot. But it turns out that Peter Shor, in '94, he found out a quantum algorithm for factor n-digit number that scales only as 72 times n to the cubic power of n. So vastly different, right? So it's really a different scaling. It's not, again, right? That's what I mentioned. It's not a 10x proven, it's a 10 to the x, right? It's just the complexity is different. So how he found out? Well, is the way that everyone does algorithm research in quantum space at the moment. He wrote down a circuit. I don't want to explain what this circuit is, but that's if you study quantum mechanics, you study quantum computation, you see that this does the job, right? And this is how he figured this out. So then if you put the numbers again, if you want to factor a 2048 digit number, this will take a few minutes on the quantum computer. And therefore, RSA is not secure, right? OK, so that shows the strength of this paradigm if we can make it happen. It's also not the application that we want to focus on, right? We don't want to break other people's secrets. And there are people working on this threat. So there's research on post-quantum cryptography being developed to address this problem. And I'm sure once we have the quantum computer, we have figured this out. But this shows the power of the paradigm. Let me actually then just dive into one more example, which is the second one, to simulate this FEMOCO molecule, because this points out in kind of the applications that we really want to have eventually, and that is worth building a computer for them. So this is in the direction of simulating physics and chemistry better. So in this particular case, there is what we call this Haber-Bosch process. And this is a way to produce ammonia fertilizer from nitrogen. And it's used a lot, but it's very costly in terms of the energy that you need for that. And there is estimates on how much energy is required for that, and it goes up to like 3% of the world production of energy. Maybe it's a little, conservatively slightly better, but it's a lot, right? So it's a big deal if you can do this better. And it turns out that nature does this better. So there is, in some bacteria, there's a process called nitrogenase, and they do this naturally. But we would like to understand this process to maybe do it artificially or to improve it. But it's out of reach to really understand what's going on there. Because this nitrogenase there's an enzyme that does it there. And the cofactor, like a key component of this enzyme is a molecule. It's called the FEMOCO. And this has like more than 70 electronic states. But then, because of this problem that I mentioned before, this is out of reach for HPC, for high-performance computing. So there are methods, people try that, but the accuracy is not good enough, right? And the insights that we would like to learn from this, they're not out there yet. With a quantum computer, we could do that. We could simulate this molecule, and then we can understand this better and just and capitalize from it. So again, what is the procedure to do that? Well, people just wrote a circuit, right? So we have to believe that this works. But I won't tell you more about this. All right, so this is the ideal world, right? Already with 200 qubits, you could get this big win if we can get there. But again, right, remember this is with perfect qubits, right? And there is no such thing as perfect qubits. Actually, the qubits, they're very noisy, very hard to control, and this is really the challenge to make these things work. But there is an idea to actually get as good qubits as we want, and that's why we believe, really we can have a quantum computer. Why it's not just like something similar to analog computing, why it's really something more like digital computing that we know works very well. And that's the idea of error correction, and for quantum computing of quantum error correction. So let me explain what this is in one slide. So first, how we model how good our qubits are, we use the error rates, right? So the error rate is very easy to understand. It's just the probability that there is an error during the execution of a quantum gate, right? So we know a quantum algorithm is a sequence of these quantum gates. There can be errors sometimes in one of these quantum gates, and this is the error rate. This happens actually in classical computing as well, though the error rate is so small in transistors that we forget about it. But of course, we can have a bit flip, right? We can have a 0 there in the memory, it goes to a 1. We can have a 1, it goes into a 0. Quantum, you can think, well, quantum is very subtle because you have this superposition, right? So you have this, alpha and beta are two complex coefficients. There are like infinitely many values for them. But it turns out that errors, we can think in a very simplistic way, is a little bit more complicated, but not that much more. We have two types of errors now. We have a qubit bit flip, is the same thing before. A superposition of alpha 0 plus beta 1 goes into alpha 1, beta 0, right? So you just change the labels of the qubits, of the basis elements of the qubits. Or you can have now a qubit phase flip, where the superposition with a plus sign turns into superposition with a minus sign. And it turns out that we can think of some arbitrary error just as a composition of these two kinds of errors. So now we can try to correct this, right? How we correct this classically? Well, the idea of error correction is to protect information by redundant encoding, right? So instead of, for example, classically having 1 bit to encode the information, we use many bits. The easiest way to do that is what we call repetition codes. For example, instead of having 1 0, we can have 5 zeros. Instead of 1 1, we have 5 1s in memory. And then if 1 or 2 of these bits are corrupted, we can still recover the information, right? We just do majority votes, right? We just see what is the majority of the bits are there, and then we get the information. Quantum mechanics is kind of the same, but much more subtle, right? Because we have to correct now bit flips and phase flips. It's a beautiful theory. Some early experiments, very exciting, where I show that this does work. I won't tell you the details, but now we have to use really entanglements to fight the effect of noise, and there is ways of doing that. Okay, but does this really work? Let me show you this plot, because this makes an important point. So this plot is, right, on the y-axis is the error rates of the qubits, and on the x-axis is the qubit overhead. What is the qubit overhead? Is how many qubits you want to build in the lab to encode each of what we call the logical qubits, which is these qubits where the computation happens there. And then there is a threshold, and this is a very important threshold, what we call the error correction threshold, which is a key number where if you're above it, it's impossible to do the error correction. It's so noisy, the qubits, that the error accumulates. There is no way to reduce the error. And then if you're below this, it's a sharp transition, and then you can do error correction, and you can do qubits. You can get qubits with as small error rates as you wish. But there's a trade-off, and that's important as well. So in this plot, I have a target. I would like to have, in the end, the output should be qubits, which are so good that I can implement gates there, and I can implement 1 billion gates before I have 1 error. And you can put the target that you want. But then given the target, you have this curve, as I'm showing you here. So if your initial qubits, the threshold is around like a little bit less than 1%, right? But the overhead is huge, right? It would be like getting to 1 million. So you need 1 million qubits for every good logical qubits. If the error rate of your qubits are smaller, right? If you have better and better qubits in the lab, for example, like around 10 to the minus 4 or 5 10 to the minus 4, then you get to more reasonable overheads of hundreds or thousands. And this is really where you want to get, right? Because we cannot, if you really have to build a million qubits per useful logical qubit, that's probably too challenging. Okay, so I'll tell you soon where we are in terms of these numbers. But before, let me just show you this slide before. So this gets much more daunting now, right? Once you put this error rate into account. So let's consider the same plot, same slides, but now with realistic 0.1 error rate for the gates. So this is hard to get, but it's possible. We have some experiments that get close to that, or even achieve that under some conditions nowadays. But now you see that once you put the overheads into account, to factor, we need 10 million qubits, as far as we know. To simulate FEMOC, we need at least 200,000 qubits. In material science applications, 100,000 qubits. In optimization, maybe 500,000 qubits, right? So we hope to get there, but it's still some way. And I want to note, I will mention this later again, but I want to note that we know that we have this application, right? We have like proofs that this would work, right? So, which is quite remarkable if you think about that, right? Because we cannot simulate this on computers, it's too costly. So really it's things that we can do with like a pen and paper, right? We have to go to the boards, use the laws of quantum mechanics, and try to figure out these applications. So you see that probably, I'm sure that once we actually have quantum computers, there will be way more applications, right? That we'll find out later. Very good, so where we are, right, in terms of quantum computing development. So we can call like these quantum computing eras. There is one era, number 1, like this gray zone. And this is what we can call like the era where the quantum devices that we can build in the lab, they are classical simulatable. Meaning that because the number of qubits is very small, like smaller than 50, or because they are very noisy, even if you have a large number of qubits, but they're extremely noisy, then we have good ways on a classical computer to simulate the system, right? So first, just for you to put into context, remember that the cost grows exponentially, right? But if it grows exponentially, but if you have 20 qubits, that's not a problem, right? So you can handle that very well. What is more surprising, but is the case, if the qubits are very noisy, if you have a lot of them, there's clever ways of also simulating this quickly. So it's really, it's like this volume, right? We must have small error rates and a large number of qubits. Then there's, after this gray zone, it starts to get very challenging to simulate these qubits, these systems. And then we get to this area that we call noisy intermediate scale quantum, where NISQ that I mentioned before. So this is this area where we cannot use even our supercomputers to simulate these quantum systems anymore. It's really hard. But we do not know if there are applications yet. Right? And this goes from like 50 qubits or so, or good qubits, up to what I mentioned before, right, 100,000 or something like this. And then later, we know if we persist, we get to this error-corrected quantum computing era where we know there are many applications. OK, so where are we today? These are some of the points. So if you have a very small number of qubits, like just a few qubits, like 1 qubit, for example, or 2 qubits, you can get close to 10 to the minus 4 error rates, which is pretty good, right? Now, if you want a little bit more, if you want to have like 10 or dozen qubits, people have built that, but the error rate is slightly worse, right? So it's getting like to 1% or a little bit above 1%. Now there is a new data point that I'm sure many of you heard about, which is this red one, where we're just, leaving finally this first era, right? And things are starting to get interesting. So this is like 50 qubits and error rates 5 times 10 to the minus 3, which is impressive to what was done so far. So I want to mention a little bit about this. So this threshold is called quantum supremacy. And this is an important milestone. It's definitely not the end goal, but it's an important milestone. And the question really that we want to answer here is whether current quantum hardware is better than classical to do anything, right? So we want to revert the game. Usually we think about we have this cool application we want to run. Let's build the hardware to do that. This we think, OK, with the hardware we have today, can we show a separation of the power of quantum computing and classical for any problem? Doesn't matter if the problem is artificial. Doesn't matter if this problem no one really cares about. But we still want a proof of principle for that. What is analogy? Well, I'm sure you all saw maybe this morning TV shows, right, where you have this guy which is really good in math, or this woman is really good in math. Well, it's like some savant, right, human being. And then there is some kind of context of this person with like a pocket calculator, right, for multiplying some big numbers. And then usually, this person is doing really, really well. And then someone else is doing the calculation, the calculator, but the calculator always wins in the end, right? And then we're always impressed, how good this person can do the math in his head. But we should actually impress the other way around, maybe, right? Because you have the human brain, this highly complex object, right? Can do all this kind of amazing things against a very rudimentary computer, right? A pocket calculator, which can do pretty much nothing, right? It can just do these calculations. But for this very specific task, it can already outbid a human brain, right? So in this language of supremacy, you could think of this as the supremacy of the calculator, this rudimentary classical computing device, over the human brain, right? This highly complex system. What we want to do is the same, okay, with quantum computers now. So what is the problem? Instead of multiplying large numbers, we want to sample from the output distribution, like we have to say, like probabilistic samples from the output distribution of circuits which have no functionality. We just choose the gates at random. What is the version of the pocket calculator, right? What is the very simple quantum device, which nonetheless is already pretty powerful for this particular task? That's a quantum computer with 53 qubits, which Google just built recently, right? And they call it Sycamore. What is the version of the human brain now, this highly complex machine, which is way better for most tests than the rudimentary one, but might be worse for one particular test? That's the best supercomputers that we have today. For example, the Summit supercomputer. This is like the classical computing savant, if you want to put like that. And what was demonstrated recently, which is pretty cool, well, that's you can, for this task, the quantum computer takes 3 minutes to solve it, okay? But you do estimates because you cannot run this on the supercomputer, and the estimates vary a lot depending on who did the estimates, but they vary from 3 days to 100,000 years. And the truth is in between, right? We will understand this better in next year or so, in the coming days. But nonetheless, even the most conservative estimate is a vast difference, right? For a particular task, even with the best supercomputer, you'll be impractical, it'll be very expensive to do that, and we can do this with this, with this tiny quantum computer. So this again shows the power of the paradigm of quantum computation. It shows we are getting to this exciting new stage. But again, right, it's not about really having value yet, so having applications that people really care about. It's a proof of principle. So what's the future? Right, so again, this supremacy is really the beginning of this noisy intermediate scale quantum. We would like to have applications, of course, as soon as we can. We do not know when they are going to be around, but it's definitely very interesting for exploration. So in the near term, instead of trying to run Shor's algorithm for factoring or trying to do one of these big applications for the future, we do not have the budget for them yet, but we can start early explorations, more in a heuristic way. So we would like to use hybrid classical quantum methods for optimization and quantum simulation. They are heuristics. We do not know if they will work, but we can try nonetheless. But they can be run right now or in a few years once we have a slightly better hardware. And really, this is like a curve, right? The better hardware we have, the richer the class of circuits we can run, and then eventually we want to get application. So this is a picture, right, from this paper by Olson and collaborators. We have the quantum hardware in the lab, and then this box with like gamma 1, gamma 2, and so on. These are gates, right? These gates, there's a class of gates that you can implement. Then you choose some class of gates, you go there, you measure them, right? This is how you get information from the quantum system. You send to your class computer, you send to the cloud. Then you optimize the next circuit that you want to implement there, right? You try to optimize some function, and then you find the next gates that you want to implement, and you keep doing that, right? So it's like the cloud or the class computer talking to the quantum computer a few rounds, and then you try to find the best you can. And this is a richer class, so you can do more with this than you can do classically, right? It's like post-supremacy, if you do it more than 50 qubits or so. So there is a hope, and there's some intuition which points out that this might give a gain already, but again, we do not know yet, right? So showing the graph again, right? So to wrap up my part, so we are in this noisy intermediate scale quantum. It's important to have very low error rate for the qubits and to have as many qubits as we want. There is this vast zone where we are now and will be in the next few years, where we do not know what, it's kind of a mystery zone, right? There might be applications, there might not be, but it's very interesting to explore. So what we know for sure is that less than 50 qubits or so, no applications are possible, and that's just because we can simulate, right, on normal computers, the quantum computer. We also know that we have more than 100,000 qubits. Applications are provably possible, right? So that's a reason enough to really push forward the technology and try to build them. And of course, the first application, if you have to bet, you'll be somewhere in between, right? We'll be close to 50 qubits, or you'll be close to 100,000 qubits. We do not know yet. But I think now it's a very exciting time to get started and start these explorations. So thank you, and now I'll give it to Eric, who tells us what AWS is doing on this space.
Yeah, thank you, Fernando, for this great overview. We are very humble about the technological challenges ahead of us in this field. But at the same time, we're also very, very excited about the long-term potential of this technology, as Fernando has laid out, with a lot of interesting applications. Over the past year, we've spoken to many customers from the chemical industry, oil and gas, financial services, automotive and aerospace, and many other industries. And what we consistently hear is that many of our customers are just as excited as we are about this long-term potential. And they're asking us what they can do today to get started and get prepared for the arrival of this technology. Well, first of all, to reiterate that point, we believe it is the right time now for customers that are at the forefront of innovation in their field to start looking into quantum computing. Quantum computers are entering this regime that Fernando pointed out, where they are not simulatable classically anymore. And customers can get started to learn about quantum computing, exploring this regime, build the internal expertise, and develop new algorithms and IP. We believe that when we bring quantum computers out of the lab and into the hands of customers, we will see an accelerating pace of innovation. And that is an effect that we have seen in many other fields. For example, also in machine learning and AI. When you think back maybe 10, 15 years ago, from an academic perspective, very little was known as to how suitable, say, a neural network, a deep learning model, is to recommend the next book that you want to read to you, or to help autonomous drones avoid obstacles. That field really took off once a broad community of developers and researchers had ready access to powerful compute and large amounts of data. And we hope and we expect to see a very similar effect taking place in quantum computing. As we bring hardware capabilities into the hands of users, and users will develop new algorithms, new ideas, new heuristics in this NISQ era to come up with new use cases, which in turn will inspire hardware developers to improve their capabilities or develop new capabilities, which in turn will attract again more users. That will lead to an overall growth of that ecosystem, which helps us to understand better the usage patterns and use cases in quantum computing, improve the user experience, and feeding back into this virtuous cycle. Now, this is something that we call at Amazon a flywheel, and we have seen it time and time again across our business, that this accelerating pace of innovation is a really powerful force. And that is why we are introducing Amazon Braket, a fully managed AWS service that brings quantum computing resources in the hands of every developer and scientist. When you look at quantum computing today, it's really hard to get started. The developer tools are fragmented and often specific to a particular type of hardware. If you want to test and validate your approach on classical hardware, you need to configure the software stack of classical circuit simulators and manage and deploy the hardware and infrastructure to run these circuit simulators on top of. And most importantly, quantum computers and quantum hardware is scarce, and only very few are publicly available. And if you want to compare different quantum computers, you have to procure with every individual provider separately, and that can be a challenge in and of itself. Amazon Braket tries to take away a lot of that heavy lifting and helps you get started working with quantum computers in an easy and on-demand model. We'll provide managed development environments that come with the most popular programming tools and programming frameworks to help you develop and build algorithms. We will provide hosted, high-performing quantum circuit simulators that let you run your quantum circuits and algorithms on classical hardware with a single API call. And most importantly, we'll provide secure and on-demand access to different types of quantum computers in an execution model that is focused on the hybrid nature of these near-term applications that Fernando already hinted at. So let's dive a little bit deeper into these different modules. And let's start with the first one. Amazon Braket will provide fully managed Jupyter Lab environments where you can spin up a notebook with a single click of a button and get started working within seconds. These notebook and these lab environments come pre-configured with the most popular programming frameworks in quantum computing, and that includes our own SDK, which is a hardware-agnostic programming framework that makes it easy to build and develop quantum algorithms. We will also, of course, provide learning resources and example notebooks that help you get started quickly. Importantly, at that stage where you build your algorithm and define your approach, customers really want access to high-performing circuit simulators that emulate the behavior of real quantum computers and let you test your approach in a much more cost-effective way. And that is why Amazon Braket will provide hosted circuit simulators. You can run circuits, as I said before, on classical hardware with a single line of code or with a single API call. The execution is entirely serverless, and you don't need to manage any of the underlying infrastructure. You don't need to install the software, and you can simply use an API call to run these circuits. At launch, we will provide two different types of circuit simulators. On the one hand, a Schrödinger simulator that is the most straightforward and most easy to interpret one. We will also provide a tensor network simulator, which is more powerful in certain situations and is easier to parallelize. You can expect that we'll be adding many more types of simulators for specialized use cases, noise models, and so on over time. And of course, all of these simulators are optimized for AWS infrastructure to give you the best performance. So for example, with a tensor network simulator, you submit a circuit to our API. Braket will take this computation, break it down into individual parts, execute them in parallel on HPC infrastructure, recombine the results, and return them to you in S3. But of course, as we said before, in this NISQ era, applications will most likely require more than a single circuit. Instead, in these applications, as you have seen, quantum computers are used as a sub-processor in the context of a classical computation, much in the same way as GPUs are used in the context of training a machine learning model. And our circuit simulators seamlessly integrate into this hybrid execution framework. So let's dive a little bit deeper into that. And let's start with the analogy that I just brought up in machine learning. So in machine learning, when, say, you train a neural network, you start out with an objective function, which is defined by the training error that your model does on your training set. And you take an initial guess of the weights, which define the exact operations of your neural network. That neural network computation is executed on the GPU to calculate the quantity, for example, the batch error, which defines the objective function that is used by the CPU to make an optimization step, update the weights, and that cycle starts from the beginning. And you bounce back and forth between the GPU and CPU. Variational quantum algorithms operate according to the exact same idea. Also here, and I should say, variational quantum computing is a form of hybrid quantum computing, and the most popular one, the most promising one. And the idea here is that you have also an objective function, which now is defined by your problem statement. You take an initial guess for the parameters that define your quantum circuit. Your quantum processor, quantum computer, QPU, whatever you may call it, executes that circuit, calculates certain expectation values that define the objective function, and the CPU updates the variational parameters and sends them back to the QPU, and that cycle continues and goes back and forth until the algorithm is converged. Now, obviously, in the latter case, for the quantum computer, executing this workflow is much more complicated than in the machine learning case. Quantum computers are highly specialized devices that sit often in laboratory environments, and they're single-threaded, they have special latency requirements. And so brokering this execution can be much more challenging than in the case of machine learning. And that is why Amazon Braket provides a fully managed execution framework for hybrid quantum algorithms. And let me walk you through what we mean with that and how that looks in practice. Users can use the Jupyter Lab environments in Braket or any local IDE that they want to define their hybrid algorithm. They send this script or file to the Braket API together with specification of the classical hardware that they want to use and the backend that they want to use and other settings that they can choose from. Amazon Braket will then spin up the classical compute, connect it to the backend, in this case one of our circuit simulators, and broker the execution back and forth as you have seen on the previous slide. At every step of the way, Amazon Braket will report out user-defined metrics to Amazon CloudWatch, where they can be visualized and you can use them to track the progress of your algorithm in real time. Once the computation is complete, Braket will write out the results to Amazon S3, tear down the compute environment so that you only pay for what you use. And most importantly, by changing a single line of code, you can actually change that simulator backend to a real quantum computer. And the user experience is exactly the same, and no other manual steps are required. At the launch of Amazon Braket, we will provide access to 3 different types of quantum computers. We have a quantum computer based on superconducting qubits from Rigetti. We have IonQ with a quantum computer based on trapped ion technology. And we have D-Wave that are building quantum computers based on the annealing principle and also superconducting qubits. All of these devices are securely connected into the AWS cloud with a dedicated low-latency network connection. And in certain cases where the latency of these hybrid workloads become an issue, we will actually deploy the classical part of the computation on AWS hardware that is co-located with these devices at the facilities of our providers. Of course, at AWS, the launch of a service is not the finish line, but it's the starting line. And you can expect from us that we will innovate rapidly, and you can also expect from us that we will have every major quantum computing technology available through Amazon Braket in the fullness of time. Now, Amazon Braket is not like any other service on AWS. I think we mentioned many times that quantum computing is a very nascent and highly complex topic, and the big challenge in the field, frankly, will be to figure out what to do with these devices and how to employ them with impact. And it's a big challenge, and we don't want to leave our customers alone with that challenge. And that is why we have announced also this week the Amazon Quantum Solutions Lab. The Quantum Solutions Lab is a research and collaboration program that allows you to work with Amazon experts in quantum computing, machine learning, high-performance computing, to dive deep into the science of quantum computing and research and develop new algorithms and benchmark them and understand the impact of quantum computing for your business. At every step of the way, our research scientists will work side by side with your team and help you also build the internal expertise to make your organization quantum ready. And of course, at AWS, it is not our goal to promote a particular technology, and the same is true for quantum computing. We're focused on working backwards from your specific business challenge and find the best solutions across all technologies. And that, yes, that may include getting you ready and preparing you for the future of quantum computing, but it also includes finding opportunities to deliver solutions with business impact today using machine learning or high-performance computing. How that works in practice is that our teams would help you identify the most promising near-term applications of quantum computing and use cases for your business and build a collaborative project plan around it. We'll then work alongside with you to research and develop new algorithms and approaches and build prototypes on Amazon Braket. But in parallel, we will also explore and develop cutting-edge classical approaches to the very same target problems and optimize and deploy them on AWS. As I mentioned before, that includes machine learning. It also includes classical and quantum-inspired methodologies on HPC. And of course, on the one hand, that has the benefit that this allows you to optimize your approach to these problems today and deliver business value for you today. But on the other hand, it is really an important step, in our opinion, to build the best classical benchmark to fairly assess and understand if and when quantum computing will become relevant to solve real-world problems for your business. As part of the Quantum Solutions Lab, we and our customers can also work and collaborate with our quantum computing APN partners that are building different software solutions on top of Amazon Braket and providing consulting services and professional services. All of them are carefully selected, have deep expertise in quantum computing, and often specializations in different application areas. For example, computational chemistry, or optimization and combinatorics, machine learning. Some are specialized on particular types of hardware. So we are very excited to welcome these companies in our partner network to work with our teams to help customers be successful with quantum computing on AWS. Of course, as we now mentioned a few times, quantum computing is a very nascent technology, and there are significant scientific and technological challenges in the field that need to be addressed. The field has to solve a number of big obstacles, a number of big challenges. And we as AWS want to contribute to this effort and help turn the potential of quantum computing into reality. And that is why we have also announced the AWS Center for Quantum Computing. The Center of Quantum Computing will be established at Caltech, which is, as you know, a pioneer in the field of quantum computing, quantum information science. And the goal of the center is to bring together researchers from Amazon, researchers and engineers from Amazon with academic institutions that are leading in quantum computation and academic researchers to collaborate on near-term application, error correction schemes and programming models, but also to explore the development of more powerful quantum hardware and technologies. We're very excited about this. Okay, so where does it leave us? Obviously, it's a long journey, and quantum computing is a marathon and not a sprint. It's going to take a while. Quantum computing is not going to change the world today, and it may not change the world in 3, 4, or 5 years. There are good arguments to be hopeful that we'll find applications in this NISQ era sometime soon, but there are no guarantees, as Fernando pointed out. Still, I think the long-term potential of this technology is so transformative and so fundamental that we would be foolish not to try to find these applications. And Amazon Braket starts in preview, and customers who want to be at the forefront of this technology and join us on this journey to research near-term applications, learn about quantum computing, and develop ways to use quantum computers in the near term should get in touch with Amazon the Amazon Quantum Solutions Lab or their account team. As I said at the onset of this talk, we are very humble about the scientific and technological challenges ahead of us here. But we're super excited about the future and the potential of quantum computing. And we're looking forward to be working with our customers to explore new ways to use quantum computers with impact. Thank you.